Welcome to everyone. I'm Tania Lopez. I'm the project coordinator of air quality, and on behalf of the WRI, we welcome you to this technical session on air quality organized and coordinated by WRI Mexico, and we will be speaking about useful air quality forecasts for cities, performance assessments. We will have a researchers from the NASA. We will also have special officers from the Ministry of the Environment from different states such as Jalisco, Guanajuato, Nuevo Leon, from the Institute of Planning and Development of Guadalajara, and also officials from the municipalities of Zapopan, Guadalajara, León, and from the Environment Secretary of Colombia. We will also have our colleagues from Africa joining us. In this event, we will be sharing with the community of practice the different methodology stages of forecasts, specifically the forecasts that the NASA creates for monitoring and the ones that most of the cities have access to. This was part of the first stage of the city project. We will also be speaking about different statistic methods and devices that we use for measuring performance over quality, and some of the speakers will be speaking about practical uses of forecasts, such as the surveys made in advance for municipalities on the associated risks of pollutants and as well as recommendations made to the people. On this slide, you can see the agenda. We will first hear from Dr. Beatriz Cárdenas, who is going to welcome us, and she's going to give us a brief background on the air quality community of practice. Further on, we will listen to the keynote lectures from Dr. Christoph Keller, who's the researcher at the National Aeronautics and Space Administration of the United States, or the NASA, who will be speaking about air quality forecasts using the NASA GEOS-CF model, which is, well, the model that they use to create forecasts that you already have access to. Afterwards, we will listen from Dr. Monica del Carmen Jaimes, who is the Deputy Director of Analysis and Modeling at the Ministry of the Environment from Mexico City. And she will be speaking about the importance of the evaluation of the air quality model in Mexico City. Afterwards, we will hear from Jair Rafael Carrillo, who's a specialist on air quality, and he will be speaking about his experience in assessing forecasts. We will also hear from Mr. Edison Ortiz, who is the coordinator of the Integrated Air Quality Modeling System at the Ministry of the Environment. At the beginning of each presentation, I will read a small CV or description of each one of the participants. So Betty, you can start. Thank you so much, Tania, for the beginning. First of all, I wanted to tell everyone that's participating today, thank you so much for participating, especially to Dr. Christoph Keller, to Dr. Monica Jaimes, and to everyone who is joining us from the community of practice as speakers. Thank you so much for sharing with us today. I just wanted to say that this is the first session, as Tania has said, this is the first technical session of the community of practice. This community of practice is, we call it cohort 1 and cohort 2, that are the cities that participated in this project, and they received the forecasts that Christoph is going to be speaking about. Now for cohort number 2, we will be adding 2 more cities to gather more forecasts, and we want that in the 4 cities of Africa, we will also be using data created by monitoring networks from non-reference devices, but rather alternative sensor devices. We will also test out the developing of a tool that comes from satellite images to identify emissions, source emissions near to the city. We will begin with Bogota, and then this experience we will be sharing with Nairobi and with the rest of the cities. And so let's begin. Let's begin with the community of practice. As Tania has said, we will be discussing several topics. One of the topics that we think are going to be very constant for us at the communities of practice is tools. We will speak about different tools, but always going back to improving forecasts on air quality. The question we all have is, since all of the cities need tools for forecast for air quality, what we are always wondering, those that have worked in developing models for air quality, but we wonder, how is it that we can assess performance? How do we know how a model is doing, and in what cases, in what areas of the cities there can be a better performance? And that's what we're going to be speaking about today. Again, thank you so much for your time, for participating. The purpose of this community of practice is that besides hearing from the presentations of our speakers, we want to hear from all of your expertise from the community, and for us to be able to open up the space for discussion. So that's my brief introduction. Thank you so much, and let's focus today on how to assess performance of air quality forecasts, and always keeping in mind that the users are the cities. Thank you. Thank you, Betty. Just a quick note before we begin with the presentation by Dr. Christoph. During the session, you can type questions on the icon that says Q&A. Please try to address your questions to the speakers, and we will try to answer the questions during the session with the help of the speakers. At the end, if we do not have enough time to answer the questions, then we will follow up on you and make sure that all of your questions are answered. As I was saying, next we will hear from Dr. Christoph Keller, who has a PhD in atmospheric sciences from the Swiss Federal Institute of Technology from ETH Zurich. And his research focuses on using atmospheric observations to further improve model constraints. He is a principal developer of the GEOS composition forecast, GEOS-GF, that I told you about just a while ago, and I pass it on to you, Christoph.
Excellent, thank you. Let me see. So I'm going to give a broader overview of the model that we are developing at NASA to do air quality forecasts. And I'm going to sort of like focus on two things. First is just a general overview of what the model does, and maybe more important, what it doesn't, but then also how we actually evaluate the forecast skills, and in particular for sort of like a local scale, at the city scale, and how we improve it, and then a little bit of what we're planning on doing, so like in the next year or maybe even further. I should say there are a lot of people who are working on this. I'm by no means the only one, but I am the lead developer of this model. But as you can see, there are a bunch of other people who are working, and then many more that contribute. And sort of like along those lines, I am sitting in an office, which is the Global Modeling and Assimilation Office, or the GMAO. And our role really is to support all of the NASA Earth observations by building the models that sort of like fill in the gaps that the observations provide. And so we develop actually a suite of different models, and they're all sort of like one general model, which we call the GEOS model. And then depending on the applications, what we're looking at, what timescales or what processes, we have different flavors of the model. And the GEOS composition forecast model, or the GEOS-CF model, which just do air quality forecasts, is sort of like one of those multiple applications of a model. But so it's sometimes a bit confusing to people because they're different models, but they all serve a different purpose. And so for air quality forecast specifically, it's really the GEOS-CF model, which is best suited for that purpose. So what is the GEOS composition forecast model? It is really a combination of a regular weather forecasting model. When you get the weather forecast, you look at the weather forecast model, and we combine that with a full chemistry model that includes all of the chemicals, all of the air pollutants. Those pollutants are typically not in a weather forecasting system because it's a lot of computational cost to run such a model. And so we have combined them into one single system, and that really is the GEOS-CF system. So in some ways, it's fairly simple, but of course, a lot goes into a model such as GEOS-CF. What I have here on this slide is sort of like a broad overview, and the model really consists, in my head at least, of sort of like three parts. One is just the science. We know a lot about how chemicals react with each other, and how they evolve and how the wind blows them around and things like that. So the science is kind of like the backbone of the model. But then, of course, we incorporate as much satellite information and other observations as well. There are sondes, data, etc. And we try to integrate all of that into the model so that we get essentially a feedback in real times, what is happening on the ground, and we incorporate that into the model. But then there are also other pieces of information which are very important, especially for air quality forecasts. The emission inventories are really a crucial piece. And so we try to sort of like get all of those things into one single model and try to stay up to date with all of them. And I should say, especially the science, but also the emission inventories, they are still developing very rapidly, and some of the processes, and in particular also with the emissions, have quite large uncertainties. And so we're always on the lookout and how can we improve it. And I think one of the exciting things about this project too is that there are some ideas and can we improve the emissions, and we would also be very interested in getting better emission information, feed that back into our model. But so in general, there's sort of like these three pillars in the model: the science, satellite information, and then emissions, in particular here for the air quality forecast. So sort of like talking a little bit about the specifics of the model. What we do is, for now, we do once a day, we run a 5-day forecast. We hope to move to making the forecasts twice a day. And I think that's probably going to happen maybe even later this year or so. But we have then a 5-day forecast. And the way that we run this is that before we do the 5-day forecast, we actually go back a day and sort of like try to incorporate all of the observations from the previous day into our model. And then using that latest and greatest sort of like state of the model, we launch a 5-day forecast. The model is obviously not infinite resolution. We have to sort of like break up the world into little boxes so that we can do the computations in all of those boxes. And the box size right now is 25 by 25 square kilometer. That may sound fairly coarse, but this is, as far as I'm aware, one of the highest resolution global models for atmospheric composition. Our focus is also not just at the surface, but it is really the entire atmosphere. So our model has 72 layers, from the surface all the way to essentially the top of the atmosphere. And we hope to even increase that. And just to give you an idea, the computational resources that are needed to run a model like that are really quite enormous. So I'm lucky that we have a supercomputer at NASA that we can use to run this, but it's sort of like the equivalent of having 3,500 computers, and you run them for 6 hours, and then that gives you one 5-day forecast. And so we do this every day over and over again. So you really need quite a bit of resources to run this. And that's also the main reason why we're still stuck at the 25 by 25 kilometer square. We would love to go to higher resolution. I think we will soon, to 12 by 12 kilometer square. But obviously, we're not at sort of like a 1 by 1 kilometer square or something like that, which I know a lot of cities would love to have. We would love to have it too, but then we would need probably 1 million computers or so, and we just don't have that yet. But then, so if we do this, we get an output, something that looks something like this. So this is surface ozone as we calculate it in our model. As I said, this is 25 by 25 kilometers square. Just to give you an idea, this is, if we take then the 72 model levels, gives you 56 million grid cells that we calculate essentially every 5 minutes what's happening in each of those grid cells. And we have a lot of chemicals that we keep track of. We have more than 200 chemical species, and we calculate the concentrations of all of those essentially in real time, and then also 5 days into the future. Needless to say, that can be quite a lot of output data. We write out more than 1 terabyte per day. and even there we're selective. But so it's quite the beast of a model in some ways, but it does perform fairly well in many ways. Okay, so we do make a lot of the information publicly available on our homepage. There are multiple ways that people can access it. There one way is to just visualize it or just have sort of like some figures, but then you can also actually get the data and use it yourself if you're interested in. So this is all publicly available. It's open source, and so we're not hiding this behind a paywall or anything like that. Oops, let me see. There we go. We're also developing some new features, which specifically we got a lot of feedback from people that they wanted some additional capability also on our homepage. So we have now new features where there's a map and you can just click on wherever you want, and then you can download the data just from that location as is produced by the model. So it's just the 25 by 25 square kilometer forecast. I will talk about the sort of like the more localized forecasts in just a second. So I should mention that for us, our focus on the model is really the entire atmosphere, because we support the satellite missions that we have. And the satellites, of course, are not just looking at the surface, they're looking in the entire atmosphere. But we do also really evaluate quite a bit the model about how does it work at the surface, or how well does it perform at the surface. And so for, how suitable is it for air quality and health applications? And there's sort of like two ways to look at this. One is how good is the model, and then how bad is the air pollution? And for me, how good is the model is really what I want to talk a little bit about here, how we actually evaluate the model here. Sorry, I have to keep this pop-ups. I don't know if you see them. So what we do here when we evaluate the model is, so there are a lot of surface observations that are available globally. And so we try to incorporate all of those into our evaluation. And I'm going to show just a few results about sort of like the evaluation, how that compares. One of them is we look at surface ozone. And when we compare our model against surface ozone from the Global Atmospheric Watch Network, the model actually compares fairly well. And so this is shown here, where we have comparisons, and I grouped them into different regions here. And I hope you can see this okay, all right, but the purple line is the model, and then the different colors are sort of like the different regions. And what you can see, this sort of like in general, our model does actually capture the observations from those Global Atmospheric Watch observations fairly well. Now, I should highlight those are by design placed in remote areas. This is background ozone that the Global Atmospheric Watch Network is measuring, and our model performs well. And in some ways, we would hope that that's the case, because the background sites, they're fairly representative for a large area, and our model does simulate a fairly coarse grid or a large area. So the two match each other fairly well, and that's actually very encouraging to see. When we look then at more local surface ozone observations and compare the model against that, the skills don't look nearly as good. And that's again expected, because we're now at the more local level. And so what you observe and what the model simulates, there may be a little bit of a mismatch in the scale. And we see this sort of like when we compare it against OpenAQ sites. And so what I'm showing here is, this is the comparison where I group it again into 6 regions. And then what we see now, the GEOS-CF is the magenta, the brighter, and then the purple, the darker, is OpenAQ. And you see that quite often the model actually is a bit too high in ozone when we compare it against OpenAQ sites. Again, those are typically more local and more in urban areas, so probably more applicable for sort of like city level analysis. What we also see is that if we only look at the afternoon, the model does perform a little bit better. And so in some ways, this is expected, because our model a lot of the science is optimized towards afternoon ozone. And we see this that if we exclude sort of like the nighttime ozone values from the analysis, in some ways we cheat maybe a little bit, but then the comparison does look a little bit better. One other thing that we know, the current version of our model overestimates the aerosols. So fine particulate matter, PM2.5, or also aerosol optical depth, or the entire column of aerosols. We know that we are overestimating that in the model right now. We know why that's the case. There's some scientific reasons why that's the case. And we are actually right now in the process of upgrading our system to a new version of the model where this overestimation should be much smaller. So where we should be performing better with PM2.5. So one of the ways that we evaluate not just the skill of sort of like the model as we run it backwards and compare it against observations, but also the skill in the forecasts is in a way like this. So this is a busy figure. I will walk through it a little bit, but what we're showing here is essentially the forecast skill of the model, both for the hindcast, so for the previous day, and then also for the 5-day forecasts, which is the +1, +2, +3, +4, +5. So essentially, how well does the forecasts work in the future compared to what was actually observed? And then we look at 3 skills in this particular case: the normalized mean bias, so just how far off is sort of like the mean concentration against the observation, the root mean square error, and then also the correlation coefficient. And then we do this for ozone, for nitrogen dioxide, NO2, and for PM2.5. So the 3 kind of like criteria pollutants. And what we're seeing right off the bat, what you can see is that the forecast scale is actually fairly flat, which means that our 5-day forecast is pretty good, or doesn't really, that the scale is not much worse than, let's say, the 1-day forecast or even the hindcast. So in other words, what we predict 5 days in advance agrees almost as well as what we predict only 1 day in advance. And sometimes that may be a bit surprising to people, but really one of the main reasons is that the forecasts are very much driven by what we assume what the emissions are. And we don't really have a great way right now of updating our emissions in real time. And so the emissions in some ways are almost baked into the cake, so to speak. So they don't change much from a 5-day forecast to a 1-day forecast. And the emissions are really one of the main drivers. And there are some exceptions, of course. If you have forest fires, we do observe the forest fires from satellite. So if there is a forest fire, and all of a sudden a satellite picks it up, it goes into our model, then that can change the forecast skill dramatically. But sort of like on aggregate, if we average over all of the forecasts from everywhere, we see that the 5-day forecast is almost as good as the 1-day forecast. I did mention a couple of times that we are very much aware that a 25 by 25 square kilometer grid cell is not necessarily representative of what you measure at an observation site. And what I'm showing here, this is actually the 3 monitoring stations in Leon. And sort of like what I overlay here is our model gives you the average over this entire grid cell, and then the observation site just measures at this one location. And so the two may not necessarily match each other. And indeed, if we compare what the model is, and this is here for ozone, what the model predicts at the given site, and what the observations are, which are in black, then you see that there's a mismatch. And in some ways that will be expected, and it can be actually sometimes difficult to really tease out how much of that difference is because of an error in the model and how much is just a representation error. But so one of the things that we can then use is, if we have surface observations, we can use machine learning to make a bias correction, so that we essentially bring the model forecast down to a local scale. And so I've been playing around with this quite a bit. But the basic idea is that we use the model forecast, and then we incorporate information such as what is the weather doing, where's the wind speed coming from, how stable is the atmosphere, and things like that. But then also, what time of the day is it, what is the season? And then based on historical comparisons, we start to discover some patterns where, oh, whenever it's really hot, the model tends to overestimate or underestimate or whatever. And so we use machine learning to essentially do these bias corrections. And when we do that, then we can actually achieve some very good matches with the observations. And then we can really provide essentially tailored forecasts for a particular site that typically match the observations much better. And this is shown here. So now the green line is the model with that bias correction applied to it. And as you can see, obviously, this now matches the observations much better. And so this is something that we have been using now quite extensively to then also produce essentially these tailored forecasts at locations of interest. And now we can essentially repeat the same analysis that I showed with those forecast skills, but now looking at the localized forecast, so at this tailored forecast instead of just looking at the broad grid cell. And when we do that, we see that our skills actually improve quite significantly. So what is shown here now is essentially the same comparisons with the skill score as a function of the forecast day. And then the bar plots are kind of like the main skill scores. And what I'm showing here in those little diamonds, these are the skill scores if we don't use the bias correction, just the regular model. And what you can see there is that now with the bias correction, with the localized forecasts, our bias is essentially 0 for all 3 species. So we get now essentially a forecast that is more or less with no bias. And that's very different from the regular model where we do have a bias, especially for PM2.5. We also see that the root mean square error is very much lower than just the regular model. And then we also see that the correlation coefficient against the observations is much better. What we see here, and I think this is in some ways actually quite interesting, is that we are now seeing a deterioration in the skill score as we go further out. And that has simply to do that the machine learning correction is better at sort of like correcting for, let's say, tomorrow's forecast and 5 days into the future. But we start to see that, for example, the correlation coefficient of our 5-day forecast is quite a bit lower than the 1-day forecast. So for the localized or the bias corrected forecasts, the longer the forecast, the higher the uncertainty in the model. But so this is sort of like the way that we like to evaluate sort of like our forecasts, in particular at the local scale. And I think this is, we repeat this analysis sort of like every once in a while to see that the model still performs as we would expect and that we're not seeing like a complete degradation. Now, one of the things, and this is, I think, kind of like my last slide here, is, those localized forecasts, I think they can be very powerful, and we love to share them with as many people and as many groups as possible. But we also recognize that we have to really work on how we can maybe make it a bit more flexible so that maybe even the end user can develop those localized forecasts themselves or can play around with them and so on. So really expanding the capabilities of those localized forecasts is a priority. And we have been working with WRI specifically on making the forecasts available to the end users. And this has been, I think, very useful. And then internally at NASA, we have also been working on porting a lot of the computation of those localized forecasts, so not the model itself, but the localized forecasts onto the cloud, with the hope that we can then share that more broadly with the community, that other people can access it and can maybe even play around with it and so on. And so that's now something that I'm working on with 2 students, actually, that they're really interested in how far can they take it, so that maybe it becomes a simple interface or so that end users can really go and dig into the forecast, the localized forecast, and see what are the factors that contribute to the skill scores and things like that, so that it becomes a bit more interactive. So that's one of the things that is really a focus now from our end, and we're very happy here to collaborate with WRI and then get feedback about what is useful, and what are the kind of like capabilities and tools that the end users want. And I think now with sort of like the cloud capabilities that NASA is developing, we have a good way to also explore that and hopefully share it a bit more easily. And this is pretty much all I have. So this is my last slide. Thanks for your attention. If you have any questions or comments, please feel free to send me an email. And I think with that, I'll leave it at here. I hope I didn't take up too much time. Thank you very much.
Thank you so much, Christoph. Actually, it was less time, so thank you very much. Your presentation was very, very clear. Thank you. I just wanted to highlight a couple of things. You said that this type of forecast needs a lot of computer processing, and we not all of us have that kind of equipment. Not everyone has the capability of doing that. And also the machine learning algorithm that you mentioned that you use for making adjustments in forecast is based on that the measured data is reliable. So that's also a message to share to our colleagues in the cities that we need reliable information so that those corrections work. And then at the end, if we have time, we will turn on the microphone and read them out. Thank you again for your time, Christoph. And we will now start with the presentation from Dr. Monica. Has a PhD in environmental engineering from the Faculty of Engineering of the UNAM. She's in charge of implementing methods for the integration, validation, administration, and analysis of the data generated by the Mexico City atmospheric monitoring system with the purpose of creating strategies to prevent and control air pollution. I pass it on to you, Monica. Would you like to start sharing the screen? Good morning. As Tania said, I work in the Ministry of the Environment, and I will present to you what my team developed for assessing a model. Mexico City's main characteristics and the main issues that we face in Mexico City are secondary pollutants, mainly ozone and PM2.5. And this is because of where the metropolitan area of Mexico is located. That is, we are surrounded by mountains, and its altitude is 1,800 meters above the sea level, and we are in a latitude where we receive sunlight throughout the year. This means that throughout the year, we have high levels of sun radiation. Also, the fact that 22 million people live here in the metropolitan area, and there are more than 6.3 million houses or households, and there are over 6 million cars circulating every day. There are 1,900 regulated industries, regulated because there are other ones that are not regulated, over 2,800 regulated commerce and services. And well, those are the ones that we have registered. But of course, there are other smaller commerces that we haven't really registered, and we cannot follow up on their emissions because there's no reliable information from them. There is a system for air quality forecast which was developed together with the Barcelona Supercomputer Center, which is coordinated by Dr. Mark Guevara. And they helped us to create a system in our cluster. They also delivered training so that we would be autonomous when it came to running the model. The main objective of our system is to be able to forewarn the population with at least one day in advance on the pollution level so that they can take their own prevention measures. It's also so that we can see high polluting events related to the environmental emergency program. Our system also allows us to assess future air quality. There is a publication on our website for 2021-2030. We carried out models to analyze if the measures that were being proposed would actually impact the concentration levels of particles and ozone. So that's what these models have been very helpful for. Our forecast system is made up by three modules, or three models rather. The first one is the WRF meteorological model that runs in the four domains that you can see on the screen. At the bottom, you can see the resolution of each one of domains. And in domain 3 and domain 4, we are only running Hermes Mexico emission model developed by the Supercomputing Center in Barcelona, and the transportation model, which is called the CMAC, which was developed by North Carolina's University in the US. All of these models are free models and they can be used by the community. We use GFS models from the US for weather forecasts, and for the burn of biomass, we use the GFAS, which was created by the European community. And this model, we can see the red flags in the model. And we can also see emissions due to fires. Of course, the fires need to be large scale fires so that the model is able to detect them. After running the models, we have post processing. And in this stage of the process, we use Kalman's filter. You know that in each one of these models, the meteorological, the emission, and the air quality model, there is an additional level of uncertainty added, and that uncertainty is reflected at the end of the forecast, where you can see that sometimes the model is not actually simulating. So by using Kalman's filter, we are able to view, well, Kalman's filter corrects data. Kalman's filter is a mathematical algorithm that reduces systematic error in data, and it's cyclical. So the pollutants that have a more cyclical behavior, they are great with Kalman's filter. We just use it for PM2.5 and for ozone because those are the ones that are more important to us, but it can be used for any pollutant, not for NO2, because we have extraordinary emissions due to the thermal power plants located in the north of the Valley of Mexico, and the peaks are so high that Kalman wouldn't be very good at simulating them. And there would be an excessive amount of concentrations on the next days. What Kalman does is look at the cyclical behavior of pollutants, and then it calculates if there's an error one day, then the algorithm tries to include the mistake the next day and it corrects the model. Sometimes it does it really well, especially when it comes to particles. That's where it is able to correct it very well, because as you know, there are sometimes outliers, and it's difficult for a model to see them out of the blue, or what we call uncertainties. There are three models. It's actually the same model. It's CMAT, but it has three different versions or three different outputs. The first one, it's called Model 0Z, that uses GFS meteorological data from time zero, and that's our backup in case any of the two other ones is not running. Model 5.2 is a model where we use version 5.2 of CMAC, and we're able to better see aerosols, so PM2.5 as well as high ozone events. It's very good at seeing them. And then model 18 said uses runs 54 hours, and that's the model that we use most of the time, and we use it most of the year. That's the one that we think it's the best one. But we also use the two other ones sometimes. We would like to merge them actually, and we are uh, working currently with the Sorcost base of California because they merge these three different outputs, and we want to see how we could maybe merge them because we use other methods such as Kalman's filters and another one that was implemented by the Barcelona Center. So we would like to see if there's a possibility of merging all of that. I'll speak now about the model of evaluation. This creates HTMLs, and through PHP, we show this data in internet browsers, and using Apache, which is another application, you're able to see it. As Christoph said, we need observations, otherwise there's no way of assessing the performance of the model. Mexico City has a CIMAT, which is a center for monitoring the weather, and it has four different areas: automatic network, manual network, meteorological, atmospheric deposition. The automatic has four stations. It measures gas and particles, and those are the stations that we use for assessing the model, as well as the meteorological network, which is made up by 28 sites that are part of those 34, plus the environmental analysis model that is not part of the automatic network. Now, this is the main menu that you can see when you access the system. You can see an overview, which is an overview that you can see every day. And then you can see reports, report 18Z, report 00Z, which are more detailed. This is the daily summary, and you can see concentrations of each season, and you can see the standard deviation of that season during that month. When the month starts, we use the previous month. So you can see the deviation based on observed data. So on the left, you can see model 18Z, and you can see ozone in the forecast model for today, 24 hours, 42 hours, that's for tomorrow, and then Kalman 24 hours with its corrections, and then Kalman 48 hours. On the right, you can see model 00Z. It's called 00Z, but it's actually model 5.2. You can see that ozone is usually greater concentrated often because it's not very good with aerosols. All of this are based on different times, and the colors also show different indexes. If there's data in red or in purple, then that's a red flag, so that we can carry out a deeper analysis and to determine whether there's actually going to be an emergency, or maybe if the model is overestimating. On the left, on the far left, you can see the probability of there being an emergency. You can see that for the 48-hour method, according to plus minus standard deviation, it could exceed the value of 54 ppbs, which is when emergencies are activated, and the likelihood of that happening is 1%. So that means that there's not very high likelihood of there being an emergency, but we use this information, we share it with the meteorological center. They also looked at observed data, and they tell us if the model is overestimating or underestimating concentrations. They are the ones who share the final forecast because they look at the systems, and sometimes because it's at a micro scale level, that's impossible to detect. Even though our model is 1 kilometer, sometimes there are some aspects that are not considered. Here in AJM, the first information that you can see is 120, and then over here you can see time. The dots are observed, and red is forecast and blue is forecast too, but corrected using Kalman's filter. So March 5th, you can see that the data was the levels were very high, but none of the models were able to actually meet those forecasts. So as you can see, Kalman adjusts a little bit higher and the observations are lower. So it depends on the behavior of the pollutant that Kalman makes its corrections. This is the main menu, but you can see the timelines of all seasons. And as you can see on the bottom, you can see the timeline of PM 2.5. We also assess mobile ozone 8 hours and PM 2.5 24 hours. And we also assess carbon monoxide and sulfur dioxide in the same menu. And you can see time series as well. They all look the same. Now, the assessment module is a little bit more detailed. So say that you choose model 18Z. That model includes evaluation of maximums, space evaluation, category evaluation, Taylor and quantile diagrams, and we use open air libraries from R and other libraries in order to make these assessments. Over here, you can see the daily maximum considering all different stations. This is from January to March 2020. You can see the dots, which are observed data, and then the lines are the different forecasts. On the bottom, you can see a table where you would be able to tell whether the forecast was good, average, or bad. And there's even a percentage good, average, or bad. It depends on the interval of 10% difference from observations compared to the model. Now, this is the categorical evaluation. Our standard is 95 ppbs for ozone, so we assess how well the model is being simulated based on the observed data, and then it also shows you the accuracy rate, the bias, etc. This is statistic methodology, which is also open air. So all of these libraries are available for you to assess the model. And we also have daily profiles. So over here, you can see how Kalman's filter adjusts the profile almost to perfection with observed data. The red line is Kalman 24 hours. So these are all of the stations and these are all of their profiles. And on the contrary, Kalman's value, 48 hours, doesn't really match, doesn't really correct. Where you can see a greater mismatch is in the stations located at the border of the metropolitan area. The stations that are located maybe towards the city center, they are better simulated. So the ones on the outskirts are not being simulated that well. And this can also be seen in this spatial evaluation. You can see the differences in observed data and model data. You can see that the darker ones are located mostly outside. And then at the center, you can see that there is less difference. And in Kalman's filter, that difference is reduced very much due to the correction it makes. And in absolute differences, it's almost exactly the same. This is related to inventories as well. Remember that what is essential about a model is inventory. So the better the inventory, the better there will be a model response. Over here in the Taylor's diagram, which is also done with open airs, it's a summary of how the model is responding. On the bottom, if it's exactly where it says observed, it means that our model is perfect, but ours is not perfect. And it's actually in a higher correlation to 2.8, which isn't that bad. And there is a standard deviation that's of about 10, maybe. And then RMS, that one are the lines, the brown lines. That's approximately 15. 15, yes. So this diagram is very useful it, to assess the model generally. I think that it's one of the best tools that we have for assessing the model. We also have the quantile diagram where you can actually see the behavior of the model. As you can see, the higher data, they're very difficult to forecast. And you can see that in the graphs. Supposedly the red line should be on top of the blue one. You can see that it's doing okay, but usually after 100, they're not simulating as they should be. Now, on the contrary, if you look at the chart on the right, in Gustavo Madero's station, those are the ones that are usually on top of the blue line. So it also depends on location whether you would have a better or worse simulation. And that also helps us to make corrections in the inventory to know that emission sources are missing, that space distribution should be improved. So all of this helps in us improving the model. We also assess errors. So in these graphs that you can see here, the QQ graphs, they should be on top of the line. So as you can see, some values are, well, here you can see the residual errors, and most of them are in the center, but there are other cases where they are not really, and that's what you can use to assess the bias of our model. Now, the model, we use it for different applications. This is an assessment of the contingency program, and it's considering different scenarios. This is the base case. This is the non-fulfillment. If not all of the different actions are fulfilled, then fulfillment. And where we have additional actions such as reducing emissions. And even after assessing in 2016, we have exceeded in some areas 155 ppb. That's due to the conditions of Mexico City. As I said at the beginning, to be able to reduce ozone in Mexico City, we would have to reduce over 70% of COBS emissions with and similar to NOx. If we reduce more COBS than NOx, then there's an increase in ozone. And that actually happened during the pandemic in May 2020 when the city was under lockdown, and we saw an average increase of ozone, not in maximum data, but an increase in average because there was no ozone consumption. Another application is the risk index for vulnerable people. This is obtained after 24 hours, maximum 48 hours of ozone, and maximum of NO2 for an hour. And we created a project with Dr. Kevin Cromer from the University in New York, and we worked together to create this risk index for susceptible persons. It was created also together with a team of SEDEMA. So this data is special for Mexico City because we're using data, well, health data related to respiratory diseases, and we combined this with pollution and with meteorological parameters to create this model created by Dr. Kevin Kruma and his team. So we let those susceptible people know about the risk so that they can plan their activities. Now, this index actually performs really well, 95% after corrections, but it's usually 90%. So all this index is done with a forecast. It's not not done with observed data. The correction is done with observed data, but we do it at noon, and we use the data from 11 a.m. to 0 hours to make that correction, and that increases reliability to 95%. So what we tell susceptible people is quite accurate, and it's helpful for them to take the necessary measures. Plus, this is also related to the WHO values. So blue between 1 and 4 meant that the levels of the World Health Organization were not exceeded. So that was useful. Of course, when it was 9 or 10, that almost looked like an emergency. And that's, well, very complicated for people who have any health conditions. Another application is that there's an application which is used for making decisions for the contingency program. They also asked me to tell you how we use the model. And as I said, we have an output. We check with a meteorological area, especially when the data is really high, when it's very high numbers, contingency level numbers. We talk to them and they tell us whether the model is over or underestimating. I apologize. I believe the microphone is off. So we, instead of 156, we will be in 144. So that's how they get that number. And that's the one that is published in our application. In the application, that's with the expertise of meteorologists, but only in those cases where we will exceed contingency numbers. On a daily basis, on a normal day, the model information, we publish it on the website and on the app as well. Only when the data is high is that we turn to meteorologists. They are the ones who tell us what to do. As you saw, outliers are atypical data, and we need to be very sure about them because we inform the people, and then sometimes their people get worried. They start sending messages, and that shouldn't be the case. That's because our contingency program makes cars not circulate, and this really affects people. People are mostly worried about not being able to drive rather than the health. That's not very good, but that's what it's like. And I can also share with you a couple of links for more information. Thank you so much, Monica. Well, we need to start with the second block of our presentation because we're running a little bit late. I just want to highlight that you have seen how there are specific metrics to assess deviation of models in respect to measured models, and we will also share information so that you have more technical information about the metrics. As you can see, well, Jair and Edison will also speak about this. One of the tools that are used the most are open air based on ER's platform. And of course, that you need technical capabilities and training in the tools, which is something that you should consider. During this block, we will hear from our colleagues that will speak about the evaluation of forecasting performance in Monterrey's metropolitan area. That will be the presentation delivered by Jair, and we will also hear from our colleagues in Bogota. Jair, he is a PhD candidate in environmental analytical chemistry from the Autonomous University of Nuevo Leon. He's a chemical engineer in ecological restoration from the Autonomous University of Del Carmen. He has a science master's and he has over 10 years of experience in the study of atmospheric pollution, characterization of fine particulate matter, and interaction between particulate matter in the respiratory system and in the statistic analysis of data. Good morning to everyone, and if there's a lot of noise, please let me know so that I can change my location. Can everyone see my screen? Yes. Good morning to everyone. I'll try to be brief so that we could use our time the best way as possible. I had divided my presentation in 4 parts: background, tools, case studies, and conclusions. I'm using a case study from recent days. Now, about the background, the metropolitan area of Monterrey is located in the north of Mexico, in the city, well, in the metropolitan area. There are 12 municipalities, and as part of the monitoring center, we have 14 stations in 11 municipalities. Our main issues are PM10, PM2.5, and we have seen an increase in ozone concentrations and some cases of NO2. According to trends in the metropolitan area, the main issue with PM2.5 is during the winter. I have to highlight that the metropolitan area has lots of activities in all municipalities, especially in Santa Catarina, in the east, and in the north, we have 2 other areas called Apodaca and Escobedo, and the whole municipality of Monterrey, where there are different activities, mostly commercial. There has been a very significant increase in real estate developments in the latest years. So we have noticed that this development hasn't been done in an organized way, which means that it's very problematic. The city is located in a semi-desertic area. There are mountain ranges that are barriers, natural barriers for dispersing pollutants. Distribution or the transportation of the pollutants goes from east to west most of the year, and during the winter and autumn, we have cold fronts. Usually they come from the north and northwest of the city. Thanks to the support of WRI and to the data provided to them through NASA, we use language R programming language through R Studio. What's great about this programming language is that it is great for statistic observations. We use tidyverse packaging that has different tools for us to carry out this analysis, and we also use the language that Dr. Monica spoke about, which is open air. This way, besides being able to visualize different meteorological parameters and air quality, we can assess the models that we use. This type of analysis have been useful for making reports, making technical reports for monitoring campaigns that we do in the metropolitan area with mobile communities, and also for creating the monthly summaries that we do with the Ministry of the Environment. Now, about forecasting air quality. We want to be able to visualize information that is shared with us through the model. So we need two things. First, we needed the information for the public. So we needed to create a forecast where we would average 24 hours of the forecast that is shared to us by the model used in WRI. We decided to broaden that forecast because most of the stations are in each one of the municipalities that make up the metropolitan area. So we're still in process of assessing so that we are able to define a smaller area for our station, and so that this forecast is restricted to that specific area of interest. We also want to expand the number of stations located in the metropolitan area because we didn't have enough information for the model to give us good forecasts or, well, to be able to assess each one of the regions. Now we do have a structure for each one of the stations. We have greater data clarity, and we were able to take the next step. We in the Secretariat are doing an internal assessment. We were observing forecasts every hour to see if the conditions help us to make recommendations to the people. We used meteorological analysis, and in the region, we have conditions of relative high humidity, especially during the morning. We have low temperature, and afternoon, the temperature is very extreme. Today, for example, in the morning, the temperature was 12 degrees Celsius, and humidity in some areas of the city was 85%. Now, the forecast says that after 1 p.m., the temperature will be 35 degrees Celsius and humidity of 30 to 40%. So it's very useful if we are able to assess the meteorological conditions that will happen when we assess the air quality or the pollutants in the air. Now, this is an example of what we assess and what we use our assessments for, especially the data coming from WRI. First, we download data. We do this at approximately 8 a.m. We download that information and we do it through language R, and we are able to select our monitoring stations this way, and we then are able to use charts or databases to fill them in with the data that we get from the forecast during that day. After that, we create a different script where we assess the behavior through time series, whether it's daily, monthly, hourly, whatever gives us more detail for being able to compare the forecast with real data. Then we use the tools that Dr. Monica mentioned during her presentation. So we assess number of emissions, bias, the correction index, and finally an efficiency coefficient, which is an index that has recently been included in the package. What we're trying to do is to see if the model is over or underestimating the real value, and if there is a match between observed data and if the values are actually very close to the data that we obtained through our calculations. Now, I am registering here a cold front, and we're showing real values in two monitoring stations. The first one is in the municipality of Caderesta. This station is close to a refining plant. So there's constantly incoming emissions from this plant. And on the bottom, we can see the time series for the SE plant, which is located in the center of the state. And this station is an urban area that has mostly houses and some services with a very light traffic. And there are mostly area source emissions. In these places, during or well, before the cold front in February, the winds come from the southeast and east of the metropolitan area. And after the cold front, conditions changed drastically, and they were coming from the north of the metropolitan area. And you can see in the time series that the model in red is in the station of Cadereyta an overestimation compared to real data. It's usually before the cold front. The model starts to reduce that overestimation after the cold front. And you can see the distribution of pollutants during cold fronts that have a very big impact in the metropolitan area. In the north, the transportation of pollutants is usually through dust and a mix of secondary pollutants as well as other pollutants that come from a region. Now, in the center, that you can see how the model is underestimating these values, and after February 17th, when there was a cold front, they now match the real values, but there's still a very significant variation. After gathering this data, we analyzed using quantiles, and we can see that the Cadereyta station is far from the real value and it shows a downward trend. That's usually when we have usually 15 kilograms per cubic meter. And that's usually because the behavior of the cold front before reaching the metropolitan area is also related to meteorological parameters, specifically atmospheric pressure. So before the cold front, there was high pressure, and this makes the pollutants be intact in the metropolitan area. And that's why we were able to measure them in all of the stations. Jay, do you think that you could maybe hurry up because we don't have that much time left? Yeah, sorry. So in the region of Obispado, you can see that the model is a bit higher, but it comes closer to the concentrations that you can see with the real values. In the case of the evaluations that were done at the beginning of August, we can see that Obispado, it was zero point 0.5 higher. The correction index should usually be 1. And if it's 0, then there's no real relationship compared to the forecast values. So as you can see in Obispado, there we're very close to the forecast value. And I'd like to conclude by saying that this model is very helpful for areas where we do not have impact from specific sources such as refining plants. Also, meteorological events do play a role, and we believe that satellite images can help us to increase accuracy of forecasts. And finally, I'd like to mention that we need more analysis done by other forecast models and of course, including more monitoring stations and complementary networks. Thank you. Thank you very much. Thank you, Jair. So we have Edison, who is the coordinator of the Integrated System for Air Quality from Bogota. He's a chemical engineer, has an MSE in environmental sciences. He's got more than 10 years of experience in atmospheric science and climate science. And in the last 10 years, he has been in charge of the model group of the atmosphere of the city of Bogota. He also advises different government departments in strategies for mitigating greenhouse effects, greenhouse gas. Thank you, Edison. Please go ahead. Hello, good morning. I like to be very brief in my presentation. I'll try to be very brief in my presentation. So I will speak about our forecast capabilities and how we have been assessing. I will speak mainly about these four things: introduction, the methodology, the results, and the recommendations for analyzing indicators. So Bogota, for many years, has had different models in both the private sector, the public sector, and the academia. We have identified that the models have identified that one of the main issues in pollution in Bogota, besides its internal sources, is the pollutants of biomass burning in the Amazon, in the Colombian Amazon, and around 10 or 8 years ago, We created the first atmospheric modeling system. It's a set of hardware and software and human talent that allows us to use different dispersion and photochemical models. In the last year, we have also been working very hard in variation and evaluation of atmospheric models, and we evaluate on a monthly basis. I will not delve into this, but we divide our models in 5 different categories. First, we have forecast for 90 hours. We use WRF-CMAC. We have another backup system that's not very good, but it allows us to focus on specific things. We use these models for policies, for decision making. There's some cases where we say that there's a big fire near the city or in the city, and we need to quickly assess that effect. Then we have models to have a rapid response to maybe find out more information about a storm that's going to arrive soon. We have identified burning of biomass as one of the main causes of pollution in the city. And due to that, we have a model for trajectories. They're high speeds, they're almost completely automated. And there was an enhancement made by the stilt model, which was an enhancement to the high split model. As part of the analysis, we have incorporated the GEOS-CF model that Dr. Christoph spoke of, plus GEOS-CF plus machine learning that we use together with WRI, as Christoph was explaining. What you can see on the screen comes from both the CMAC model and GeoCF of yesterday. So with GeoCF, we download that information daily, and then we say zoom in our area of interest. For us to be able to look at the evolution of forecasting, we use time sets. This was yesterday. I didn't have time to get today's, sorry. And you can see the behavior of temporary sets for the next days with each one of the models that we have, as well as the location of the stations. So it's true that in some stations, most of the models have a very specific behavior. In the model for PM 2.5, the behavior of emissions or other meteorological aspects that are difficult to model make it difficult, or they cause a mismatch between our forecasts and real data. About the methodology for verification and validation, we use 5 models. These are the 5 models that we have parameters for, and these are the tools that we use for our forecasts, and then we use them in each one of the stations. Not all of the stations do data mining because usually they are all new. So we are not able to extract that data because we maybe do not have one specific pollutant. About performance indicators, well, us who do this kind of work know that there are so many, but each one of these indicators allows us to know and to answer to specific questions. I'm sharing them because I know that these are just some of them. There are many others. We just choose the ones that help us to establish the best analysis, the best global analysis of the models. So what we do is we take all the results from the models and then we share them, we extract them, and we place them in the stations. We create a single database, and that database is used both for validation, which is how the phenomena was represented in the past, and verification of forecasting. We usually use open air, but we have also developed together with another group from the Ministry of the Environment our own developments that help us to well assess other models that are not in open air and have a solution that's different to that provided by open air. So the tools that we use are always the analyses of temporary sets, tailored diagrams, the hourly behavior of performance, the distribution of those indicators, and creating a validation system that's very robust so that we can create that evaluation in a more simple way and in a more periodic way. When we talk about validation, we have validated a phenomenon for burning biomass.
Entonces, en este primer evento donde tenemos quema, digamos que unas altas emisiones de quema.
So we can see that high levels of emissions of biomass burning, they were represented with a significant increase in concentrations. And we are expecting, well, the impact of the second biomass burning in the region. And we haven't seen it so far, but because of times, because of the lag of emissions and their impact, we could see them in the next day. So part of the variation of the models will be recorded in the representation of this phenomenon. And for validation, since this is something that we're just creating now, we are only beginning to start the work of validation. Now, for biomass, I think there are 4 stations that have different characteristics. The first one is a station in the city center that has the best spatial representativeness. The second one has a high local emissions influence. And the other two show the best and the worst performance of corrections made to the GEOS-CF model. So I will focus on the GEOS-CF model because that's the one that was presented by our colleague Christoph at the beginning of the presentation. And you can see that the pink line over here, the GEOS-CF model is very good at representing observations, which are red lines, except for biomass burning. Surely this was because there was an underestimation of emissions generated by those, well, by the burning of the Amazon forest. But after that, the median seems to be very similar between what was observed and what was modeled. If we looked at GEOS-CF data without the correction, even when Christoph was saying that for South America, it was usually overestimated. For Bogota, in most of the models, it's underestimated. And this is because of topographic situations and also because Bogota is such a large city. So there's a very high impact by local emissions that are not correctly represented in the GEOS-CF model, and you can see them locally in the stations only. We use the index of fulfillment, which is the last column, and GEOS-CF model with machine learning is even better during this season compared to the local models after being corrected. But there's still restrictions for each one of them. So the indicators are low because we're analyzing 8,000, 7,000 pieces of data on a daily resolution. So what we want is that with validation models, we will begin to build a platform where we can verify forecasts, where we can verify how well we are forecasting the models. And we are based mainly on two experiences from the NOAA and the EPA on how performance indicators behave, specifically speaking about bias. And we're speaking about observations from average profiles. And on the European side of things, it's also about representing performance indicators in a chart in the future so that we can see what is the capability of that forecast. Together with the Center for Forecast and Modeling in Bogota, which is a center that does statistics and analysis, especially on environmental matters. And you can see that both the errors are spatially distributed and also in times because our model is underestimating at night. So we're trying to find out whether this is related to emissions or the weather conditions and well, other tools that you can see over here that help us to report these indicators, these performance indicators. So yes, we have been looking at this from simple indicators, and now we are expanding it with the help of specific professionals. And now the task should be to automate these indicators in order to assess the performance in a periodic way and to make corrections in a more reactive way if it's necessary. Now, as far as recommendations go, all indicators can have acceptance criteria. Some of them don't have them, but it's important to always look at temporary behaviors, at temporary sets. When we take a look at them, we can see whether the model is working or not. In practice, there might be a lot of performance indicators, but we need to choose some specific ones that help us to answer specific questions. So if I'm going to be measuring biomass burning, then I need to decide what indicators I'm going to be using for my forecast so that I don't have a breadth of 70 indicators and analyzing them at the same time, which will cause confusion and will cause, well, a wrong explanation of the performance of the models. In all presentations, performance indicators are key for identifying improvement opportunities in model configurations as well as in the quality of input information, whether it's methodology or to see if I am actually measuring what I intended to measure in the first place. And regardless of the indicators being good or bad, there should always be an analysis carried out by professionals because maybe the indicator is just average. And that's, well, what happened in Mexico City as well, that usually professionals that use these models for air quality and meteorological aspects, it's the professionals who decide how they're going to correct it, whether it's qualitatively or quantitatively so that they can have a better forecast, because in the end, this information is shared with the rest of the people for, well, general purposes and also for determining when there are emergencies. Thank you very much. I would have liked to share so many other things about what we do in terms of modeling, but because of time, I decided to just focus on the validation of forecast models. Thank you very much. Thank you. Thank you so much, Edison. Maybe there will be more opportunities for you to talk about model systems in Colombia. If the participants from the practice communities could share their opinions with us, specifically speaking about evaluating forecasts of air quality. So, would anyone like to participate? You can turn your microphones on. Would anyone like to comment? I think Juan Parra raised his hand.
Hola. Bueno, Betty, adelante.
Betty, yes, go ahead.
Juan dice que no tiene opción de micrófono, pero si a lo mejor Juan nos puede escribir la pregunta.
Maybe Juan can type the question because I don't think his microphone is working.
Yo aprovecharía para hacerle una pregunta.
I'd like to ask a question to Christoph.
Como bien lo dijo Jair, hay algunos
As Jair said, in some cases, the cities, well, when the correction was made with machine learning, the cities in cohort 1, they shared the databases that they had. So some cities throughout this time, like the case of Bogota, who had very good data, and we saw that some other cities didn't have enough data, or the quality of data could have been improved. So now that some cities have been able to generate better data, do you think it's possible to maybe make a correction using that data so that we can do, machine learning with enhanced data that we have gathered now?
Yeah, I think so, and that's it's actually one of our hopes, is that we can make it a bit more interactive so that people can explore it, that they can, instead of having to send us the data and then we have to do it, and we almost have to make a judgment call, yeah, this is good or this is bad. But it's much easier for them to just say like, hey, here's my data, and then they can, with one click, can explore it and see like, oh, this works, or oh, I'm a bit nervous about this, because that's always better when the local experts look at it and say like, I'm happy with this, or we need more data, or whatever it is, right? So that's our hope, and that's kind of like what we're now hoping to accomplish in this second stage, is that we make it even more open, accessible. So yeah, but yeah, of course, once the data is available, and once there's more data in particular, this should work better for sure.
Muchas gracias, Christoph. Aquí también, bueno, justamente, perdón.
Thank you very much, Christoph. If you're not able to open your microphone, then you can type your question. There's a question for Dr. Monica asking about the resolution of the model. The resolution of the model of domain 4, which is where the metropolitan area of the Valley of Mexico is located, is 1 kilometer times 1 kilometer, and the inventory is also adapted to that resolution. I have a question. Yes, go ahead. I wanted to ask a question to Dr. Christoph. What is necessary for a city to participate in using machine learning and your model? Because after looking at what Edison did, maybe Mexico City could participate in this specific part of your model with machine learning?
Yeah, I mean, right now, what's necessary is my email address, and we don't like that. We would like it to be more open. So that's what we hope to accomplish in the second step, is that everybody can do it essentially themselves. That you know, if you have the data, you can say upload it, so to speak, to the cloud, and can do it yourself with one click instead of me having to do it. So yeah, that's what we hope, that we can do it more openly. So hopefully in that second step, we will get there. Now, having that said, right now I do have 2 students who are working on this. And so, you know, you can send me the data, and then I could have them sort of like look at this, and maybe we could even do this as the pilot so that they can explore sort of like those tools that we're developing, and using that data as a real use case. But that's an option. So, you know, feel free to, or actually for Mexico City, the observations are publicly available. So I can make this sort of like one of the test cities that we're using to test some of the new tools.
Thank you.
Thank you. Thank you, Christoph. So I guess Monica will contact you, Dr. Christoph. So many of you are now panel members, so you should be able to turn on your microphones and your cameras if you wish to. So if you have any questions, just raise your hand. So maybe you can share with us a plan of how to assess your forecasts. If you wish to do that, that's okay. And if not, then you can also send us questions to our WhatsApp chats. We already created one, and we will invite you to, sorry, there's some background noise here. We will also invite you to Google Classroom. That's where we're going to be sharing all of our information, and you should be able to access the videos of the sessions, the support videos, as well as the presentations, and also support information that is available on metrics that are used and statistics to assess forecasts. So we can finish the session if there are no more comments. And thank you very much on behalf of WRI. Thank you so much for participating in this webinar.